Okay, well, it's okay with you guys. Let's do both topic 2 and 3 today. Because really, topic 2, as I was looking over, I don't know why I made 2 different topics for this. Because really, you don't need me to add much. Topic 2 is I'll just look at some pictures and read some words, and I'll add a little bit. But you guys know most of its definitions by now, don't you? Right? Like a system. I mean, the system has so many different definitions, but from like a physics definition, I mean, 2 or more objects that interact with each other is pretty bland. That doesn't really add a whole lot. So basically, just consider it as either you're on the inside or you're on the outside. Either you're within the system and we're going to consider you and you're part of the circle of trust, or you're on the outside of it and you're not part of the system. Really, that's the idea, right? Like, if we considered our classroom to be a system, then all of us are within the system and everybody outside the classroom is not part of the system. And the only reason why this matters is so that we can talk about different types of systems, the open, closed, and isolated. Do you guys feel like you know these words pretty well? Yeah, I'll breeze through it then. Open is like the open door. You and I can go in and out. We're made of matter. Perfect. Energy can also go in and out. Closed system, put a lid on the top of the thing. Closed system, put a lid on top of it. Now it's like closing the door. Now we can't go in and out, but energy still moves, right? Isolated system is more of a hypothetical. We actually really can't achieve a true isolated system due to laws of thermodynamics, which state that energy is always going to transfer from something warm to something cool. So we're always going to lose some sort of energy. But for the most part, we're going to actually assume that we're dealing with the isolated systems, even though we probably are. What does that mean we have to ignore in physics? Say that louder? Yeah, that's what I was going for. Yeah, we have to ignore the fact that friction is going to exist sometimes. We just have to pretend that there's not going to be a loss of energy to that. So, another picture, another picture, another picture. I don't remember what I was going with these pictures anymore, but you guys have the gist of it. Okay. Oh, hey, they're here. I think. Yes, we have a connection. Hey guys. You didn't really miss anything. We just talked about the words isolated, closed, and open systems. So, you just had problems with Wi-Fi there? That's so strange. Okay. Okay, well, why don't we just pick it up here? Basically, if you guys feel like you got the hang of the words open, closed, and isolated, that's as far as we got. So, okay. Okay, here's what I mentioned just a second ago, the law of thermodynamics. The first one's the main one here. This is really key here. The total energy of an isolated system should be constant. Remember you're on your formula sheet, I talked about how we're going to start covering some more of those like key physics principles. The first one I think was like uniform motion, the second one was accelerated motion or something like that. I think we're up to like the fourth or fifth one here. We're going to talk about laws of conservation of energy, because that's basically what the first law of thermodynamics says. Energy should only be transformed, but it can't be destroyed or created. You can just have energy show up out of nowhere, and you also can't just have it disappear all of a sudden. Okay. Even when you think that it's disappearing, quote unquote, with fingers, you're really losing it to friction or some sort of other form. Okay, that was easy. That's kind of why I thought we should maybe do 2 sets of notes today. I have no idea why in my infinite wisdom years ago when I made these notes, I made 2 sets of them. But that's just going to be good. It's smart. So, anyways, let's do tomorrow's notes today, and then we can give you a work day tomorrow. So, sound good? Okay, so this set of notes here is going to focus basically on the concept of conservation of energy. Most of this is actually examples. So the first set of notes, topic 2, is just all do you know your definitions. Now we're going to do some math calculations. Do you guys recognize the term mechanical energy? Is that something you've been told before? I'm sure if you guys were in my class last year, we mentioned this. If you guys don't recall, mechanical energy basically is a generic term for like the sum of all energies involved, right? Like that's actually literally what's written there, right? So typically the energies we're going to be considering are kinetic and potential. Kinetic being 1/2 mv squared, potential being mgh, or the new formula we learned last week, which is the spring formula, which is 1/2 kx squared, I think it is. So pretty much that's it. Those are our formulas we need to use. So you're going to have some sort of those 3 formulas, which are categorized in 2 categories. So, This is kind of important. They put this on the diploma a lot. Do you get the concept of isolated, closed, and open based on how things are conserved? Isolated systems, matter is conserved, and energy is conserved. Basically, that's that theoretical nothing can transfer whatsoever. You isolate your thermos. More than likely, you're working in a closed system where matter should be conserved. You're not losing any mass because the door is closed or the lid is on the beaker. But yes, energy can still transfer. Open, neither of them is conserved. So, there are laws of conservation of mass and energy, both independently, but they do presume that you don't actually have an open beaker so the stuff can escape. That makes sense? Okay, let's do some examples. So, here's the math for the day. You are on a toboggan on the top of a 23.7 meter hill. We actually don't even know your mass because we didn't weigh the toboggan and you before you left. You know what? It doesn't really matter because we can still solve this. The question is, how fast are you going when you reach the bottom of the hill? So, if you need to, draw a bit of a sketch just to kind of take stock of what's there. Here's your hill. You're at the top of the hill on the toboggan with your friends. Keep drawing. Actually, wasn't bad for me. And literally the only number I give you is that you need to know how tall the hill is. That's it. We've done this before if you were in my grade 10 class. So you guys in grade 11, do you remember what to do? Any ideas? You kind of have to make your own formulas up. Like you have to merge your own ones together. What sort of energy do you have at the top of the hill? Potential. Yeah, gravitational potential, right? So when you begin, you're going to have gravitational potential energy. And when you're done, will you have any gravitational potential left? Well, no, you're at the bottom of the hill, relatively speaking. So it'll ideally all convert into kinetic energy. This is sort of a scenario where this is what, even when you were in my course, maybe even review earlier, I pointed out, like, this is the sort of thing that makes physics challenging, is you're not just using one equation independently, you're kind of merging them together, making your own formulas. Why is mass irrelevant? Yeah, you guys can visualize that. Awesome. Okay, so this one's pretty straightforward. You got your 9.81 because you're on Earth. You know your height. You know your 1/2, and you just times by 2 and square root it. You got your answer. It's actually pretty straightforward. Is this actually how fast you'll expect something in real life to go, though? Probably a little slower, because what we haven't accounted for is that you're going to lose a little bit of energy due to friction. I got 21.6. Cool, we're in agreement. Ta-da. You guys good? Okay. Alright, let's try another one. This is one that we really wouldn't have expected you to have before from, like, say, grade 10 or review unit. You've got a slingshot, but I'm giving you the spring constant and the distance it gets pulled back. We want to figure out the maximum height the rock could reach. So, again, we're going to be merging some formulas together. Before you just maybe hop into it, though, it doesn't hurt to draw a quick picture just to make sure you understand what you have in place. Here's you. You are shooting a slingshot, not very good at drawing. It's a slingshot. And you're going to shoot it straight up in the air. What sort of energy do you have when you're shooting it? Is it on? You have the potential energy of the spring. Does that make sense? Right? Like as you're pulling back, it's not in motion yet. So at this point here, you have the potential energy due to the spring of 1/2 kx squared. What's going to happen to that as soon as you let go of it? What does it get converted into? Kinetic. That kinetic energy makes the slingshot thing go in the air, and then at the very, very peak of its trajectory, it doesn't have kinetic anymore, right? It would then have, like, again, potential, but this time the potential you have is mass times gravity times height. So we don't actually have to calculate the kinetic energy in between, right? Because what ends up happening is the spring turns into kinetic, the kinetic turns into gravitational potential. We can just go right from one to the next and make a formula that says our 1/2 kx squared is eventually going to turn into mass times gravity times a change in height. And I want to point out that I'm writing it with the delta H notation here for a very specific reason. When you shoot this thing, you probably didn't shoot it from directly on the ground, did you? Right? So all we can do is we can figure out its change in height. We can figure out from here to here how much change in height there would have been. Does that make sense? Right? Unless you literally were like laying on the ground. That seems kind of strange. So. Alright, so 1/2 of 60 times 0.85, don't forget to convert that one, equals 2.5 times 9.81 times our change in height. Quick thought here. When you're working with kinetic and gravitational potential, I would say almost all of the time your mass can cancel. I can think of one example that we're doing later, I believe, where you probably don't want to cancel mass. Yeah. But if you're using the slingshot, like the elastic formula part, you won't be able to cancel mass because there's no mass in that formula. So don't always just try to cancel mass off because that's not always true. Anyways, take 2.5 and 9.81, divide them on both sides. I'm going to guess you guys can handle this. And that times 60 times 0.85 squared. Divided by 2.5, divided by 9.81. Oh. Did you guys get 0.88? Yeah. I feel like that just seems like such a small amount of number. This is a really wimpy slingshot. Well, maybe I just made poor choices in numbers to use here. Either the spring is like a really wimpy spring, maybe the mass is too big, 2.5 kilograms. I think that's too heavy of a rock, perhaps. It's a pretty heavy rock. Anyways, you guys get the concept of how to solve it? Okay, one last thought. Let's say that they told you that you launched it from like 0.3 meters above the ground. If I didn't want the total height above the ground, you would need to add on a 0.3 meters if I gave you that value, if. Does that make sense? All we know right here is we actually have the maximum height above where he launches it. If he launched it from 10 feet above the ground, it will now be 10.88 meters. Wow. If he launched it 10 meters above the ground, it would be 10.88 meters. Does that make sense? If he launched it from 1 meter above the ground, it would be 1.88 meters. So all we know is how much extra height it gets, not the total height it's at. Make sense? Cool, moving on. Okay, on Thursday, or maybe even before then if I get the stuff done, we're supposed to do a lab, where the lab is really not doing anything, it's more just analyzing video. We're going to redo a video of the pendulum lab. I didn't actually videotape it, but it'll take all of 30 seconds to take a video of the lab, of the pendulum going back and forth. And one of the things that we can calculate on a pendulum is what is the maximum speed of the pendulum. And that's actually what you guys are going to do on your lab exam project. Let's find out how fast it's actually traveling. So let's draw a quick picture of a pendulum going back and forth. As the pendulum is right about here, you can pull it back till it's about here. And it'll kind of swing like that. Where is it going to have its greatest speed? Right at the equilibrium point at the middle, right? So hopefully it'd be an agreement that this is where the velocity max is going to end up being. Is there a velocity here and here and here along the way? Well, sure. But right here where there is no more restoring force, this is where it's sped up as much as it can. So. Well, in terms of the setup, let's draw a few more things in. It says that we have a 35 centimeter long string, so it means that this is 0.7 meters, 0.75 meters here. And it also tells you that it's been pulled back this horizontal distance here of 0.35 meters. Last thing we need to know, this thing is 100 grams, so let's call that 0.100 kilograms. There's our values, that's all we got. Okay, so let's talk about different scenarios. When we start right here, what sort of energy does this thing have? Potential, due to gravity, right? So when we start, we've got some potential energy when we begin. Right down here at the bottom, does it have potential anymore? Well, relative to the floor, wherever the floor is, sure, I guess it does. If the string were to break, this thing could fall further still. But we're just going to have to say that our change in height is going to have to be based on like this as being like the lowest level we get. Does that make sense? Like your perspective matters. Is it like even though I'm standing on the ground, could I fall further down? I guess sure I could fall into the basement of the school if it was a basement, right? Or you can go more towards the center of the earth. So you do have to kind of like put the floor at some point and say that is where the 0 line happens to be. Okay, well, if at this point right here it no longer has potential relative to what we're considering, then all it has at that point is kinetic. So this is very similar to our first question again, right? All of your potential will turn into your kinetic, and right off the bat, you can actually cancel your mass again. So g times your change in height will be 1/2 of v squared. There's your next formula. Well, we only need 2 things, gravity and your change in height. We don't have that though. Because our change in height, if I can try to label this nicely, is going to be from here to here. That's our change in height. See the issue? Do you guys remember how to solve this? This is on your test, actually. Something like this. If you have, it was on your assignment too, it was the wrecking ball question. See how there's like a right angle triangle right here? What we need to do is we need to use Pythagoras' theorem and solve for, what I'm going to call this side over here, x, and find out how far it is from here to there. So take 0.75 squared and minus 0.35 squared. That'll give us this height right here. I got like completely irrational 0.66 number. Something like that. Is that the height that it goes to though? Good, years well ahead of me. Because from here down to the very, very bottom, that's 0.75. So to find this little bit here, it'll be 0.75 minus 0.66. That's actually a change in height. So I have a change in height, if I just write it off to the side here, of, I got 0.086675, etc. That's good on that? Cool. At that point, you just got to plug it in here. So times by 9.81 times by 2 and square root, and you've got a velocity of, with sig digs, I got 1.30. Does that make sense? You guys able to get that? Okay, we're going to do something similar in our lab. I'm going to give you a video. We're going to tell you how far back the pendulum's been pulled. We'll tell you the string of the pendulum. And we're going to use Tractor software and try to calculate the speed of the thing as it's traveling through the pendulum, which we didn't actually do last time around. So, like I said, we're going to kind of redo 3 previous labs and solve for stuff that we just didn't do the first time through. Okay. Hopefully this one kind of looks familiar. We did questions with pulleys like this at some point before. Again, we can actually solve this question not using dynamics, but using energy instead. almost every question that we've done in the last 3 months, you can probably use energy for, if we assume that there's no loss of energy due to friction. So, let's talk through this one, because this one's a bit strange when you've got the pulley system going 2 different ways, right? Because when we solved this one before, we had to consider that there was like a force of gravity going this way, but there was also like a force of gravity going this way, and that like the blue box wins over the yellow box kind of thing. But we're not going to use forces. We're going to use energy instead. So let's write it a little bit differently though. Let's write about the energy that we have before, the total energy, and then figure out how much energy we have after. I'm just going to like write it out a little bit more implicitly, or a little more explicitly this time.
To the following students, please come to the office. Greg Burrows, Tia Davis, Sheridan George, please come to the office.
Okay, consider these 2 boxes here, and let's assume that it kind of says that this box right here, the yellow one, starts on the floor. So before we begin, what sort of energy does the yellow box have? None, really. It's not moving. We haven't let go of the system yet. It's also on the floor, so literally the yellow box has no energy it's contributing to the system, relatively speaking. The blue box has some energy it's contributing. Does that make sense? It's contributing some gravitational potential because it has the ability to fall 3 meters. So before we begin, I'm just going to make sure I'm clear on this. We have the mass of the blue box times gravity times the change in height of the blue box. That's all the energy we have to begin with. And I'm throwing little subscripts on there just to make sure that I'm clear because they have different masses. This is going to be the example where sometimes, you know how I said you can just cancel off all your masses? We're not going to today. Not on this one. Okay, so let's say you let go of the system. If you can visualize it, what's going to happen is the blue box is going to come right about here by coming down, and the yellow box is going to move up to this location. Can you visualize that? So let's talk about the yellow box first. What will happen to the yellow box? It's going to be moving up, so what is it going to have? Well, it's going to have some potential energy, but it's also moving. Does that make sense? And because it's moving, it also is going to have some kinetic. So the yellow box will have some extra height to it because it's now in the air, and it's also in motion at that point. So it will have its own potential and its own kinetic. But we're not done, because the blue box is now sitting down here. Now the instant before it crashes into the ground, it was still moving though, wasn't it? So we also have to account for the fact that the blue box was moving. However, does it have any more potential left? No, it's used it all up. So you see how the first examples I did maybe were a little bit simple, and all of a sudden I kind of hit you with one here that you can't just go boop, boop, cancel, we're good to go, right? Like there's a little more work to this one in terms of the setup. So one more time just to make sure you're clear on how we're starting. Before we began, really the only energy in play was the blue box had the capacity to fall. So the mass of the blue box times gravity times the height of the blue box is where we're at. After scenario, the blue box has now fallen, and so it has lost its potential energy and has turned it into its own kinetic energy. However, there's more at stake than just the blue box, because the yellow box has now gained some potential energy, and the yellow box is in motion as well. So far, so good. Okay, so let's write this a little bit neater with some numbers in there. Oh, by the way, I guess I should point out, you guys are all clear that we can't just start hacking off masses everywhere, right? Because they're not equivalent. Even though there is a mass in every single one of these terms, it's not the same mass, right? So we can write it out like this then. The 12 kilogram box times by gravity
Ethan Greer, Zelwyn Hugo, please come to the office.
Times by its 3 meter height, that's what we have to work with. Well, it's going to equal the yellow box's information. The yellow box was 7.5 times 9.81 times, what's its change in height? Well, I guess isn't the yellow box going up by 3? So its change in height was 3. Okay, well then the yellow box was 7.5. Velocity of the yellow box. We don't know that, do we? And then for the other one, the blue box, it's, what is it going to be, 12 times the velocity of the blue box. So in a way I have the velocity of the yellow box I'm missing, and the velocity of the blue box that I'm missing. It appears as though I have 2 velocities I'm solving for. You're shaking your head no. Why? Yeah, they're the same. That makes sense. However fast the yellow box is moving is how fast the blue box will be moving. You know what I'm going here? So we actually can get rid of the subscripts, because they're moving the same speed, should they not? They're both attached to the same string. So we can get rid of the subscript here of b and y, and just figure out the velocity of either of them, because the velocity of the system should be the same. Okay, so to solve this, need some more room here. Okay. Let's deal with this section over here mathematically in a second. How do I get rid of this guy right here? How do you eliminate this bit right here? Subtract the other side. Okay. So I'm gonna type some numbers in here. If I do 12 times 9.81 times 3, and then I subtract 7.5 times 9.81 times 3, I have a change in energy of 132.435. So I brought that to the side. Is it going to follow that? Okay. What's left over is 1/2 of 7.5 v squared plus 1/2 of 12 v squared. This is the spot that a lot of kids get stuck on because they're not really sure how to put that together. Okay, 2 thoughts here. One, you can factor, because you literally have a v squared in both terms. Or 2, 1/2 of 7.5 is just some number, and 1/2 of 12 is just some number. They are like terms, you can put them together. My preferred method though is going to be to factor. So I'm going to factor out a v squared. So I'm going to write it as 132.435. See how both of these have a v squared? I'm going to factor out v squared. And if I do that, it leaves me with 1/2 of 7.5 plus 1/2 of 12. Does that make sense from a mathematical algebra point of view? All of this stuff that I factored out is just some number.
Breakfast. There's no more muffin stuff.
Roseanne Mandel, Logan Markland, James Cody,
Thanks, guys.
please come to the office.
1/2 of 7.5 plus, so that's 6, I guess. I have this whole thing as being 9.75, so we'll divide this by 9.75. So I end up with like 13.58 repeating equals v squared, and square root. I got 3.6855 and so on. I was able to replicate that. So with sig digs, either of the boxes is moving. It looks like I'm limited to 2 sig digs by that 3 meters. So let's call it 3.7 meters per second. Is it able to follow that? Okay, I want to point one quick thing out. I didn't want to stop at the time. Maybe I should have. A common thing kids might try to do is they might say that this is negative. Okay. But that's, let me try to explain why that's incorrect here. Right here, your potential energy was 12 times 9.81 times 3 meters. The 3 meters being the 3 meters that it could fall. And it did fall those 3 meters. Does that make sense? But I'm not going to make this one be negative 3 by saying, well, if this one went down by 3 meters, this one went up by 3 meters. And here's the rationale why. It's not about the fact that it went up the 3 meters. It's that at this point, how far does it now have to fall? And it can still fall 3 meters. So don't make this a negative 3 because of the fact that it's gone up by 3 meters. Really, what's happened is it now is 3 meters in the air. It has that same 3 meters with which to fall that the first one did. Does that make sense? So even though for most of what we've been doing in kinematics and dynamics, I would tell you make this be positive and this be negative. But do you get where I'm going here? This box, now that it's up here, yes, I know it has gone up in the air, but when we consider its potential energy, it has that potential to fall back down the 3 meters again. Right? So because of that, now that it's in the air, if that rope were to get cut, how far would it fall? Well, it would still fall the 3 meters. Right? The 3 meters that just went up, it would come back down. Any questions on this one? This one becomes a lot more challenging, obviously, just when you got to keep track of different boxes within the system. We're good? Okay, I think this is my last one, right? Yeah. Okay, so there are some questions then that you can see, we've solved these types of questions before using kinematics and dynamics. You can also use energy to solve pretty much any kinematics and dynamics question if you can kind of wrap your head around how to keep track of things. Again, assuming no loss of energy due to friction. This is the type of question that we did way back in our first unit, and a lot of people hate this question. This is the one where you take a rock, you throw it up in the air, and we want to try to figure out, how fast the rock is going at a certain point. This was essentially, remember our Nerf gun lab? This is essentially the Nerf gun lab trying to solve something like this. So what I'd like to do is first solve it using kinematics, and then on the next slide, if we have enough room to kind of put them all in there, then let's try doing it using energy, and hopefully we'll get the same answer twice, and then we'll call it a day. So let's start using kinematics here. When this rock gets thrown, what we get to know is the initial velocity along the hypotenuse was 16 meters. We get to know that this is 30 degrees. And that's about it so far. 2.5 seconds later, we're going to try to figure out its speed. I actually don't know whether it's on the downward amount or whether it's on the upward amount. I don't know that yet. Okay, well, the first thing we would have done on, like, say, our Nerf gun lab is we would have drawn a little bit of a vector triangle. We would have said this is 16, and we would have found the velocity initial in the y direction and the velocity initial in the x direction. We would have solved for both of those. So this would have been 16 times the sine of 30, and this would have been 16 times the cosine of 30. Oh, it's 8. That's nice. And this one was 13.8564, etc. Any issues so far? Okay, well, 2.5 seconds later, I don't know where the rock happens to be. And we don't actually need to know exactly where in its flight it happens to be. It could have been here, it could be a little bit at the top, it could be here. It might even be like down here, perhaps. That really doesn't matter yet. At the end of the day, though, to find its final velocity, we would need to make a triangle of its incoming trajectory. You guys recall how to do this? Where later, we need to know the velocity in y, but like the final velocity in y, and we have to know the final velocity in x, and we have to resolve for a new hypotenuse. Make sense? What's the velocity final in x going to be? That. Because is the x velocity going to change? As long as we're assuming no friction? No. So if we were to draw like an exit triangle where here's the thing later, we know that the velocity final in x is still going to be 13.86. No, what is it? 856? That hasn't changed. But what we lack is the velocity final in y. We need to know what that happens to be. So let's consider some of our velocity numbers, or some of our y direction numbers. Our velocity initial in y, we calculated, was 8 meters per second. We were given time. Time was 2.5 seconds. We don't know how high in the air this thing's going to be, but we do know one more thing in the y direction. Acceleration due to gravity, negative 9.81. That should be enough to find a velocity final in y. We can skip going through distance. We can just find the formula that involves all four of these things. So quick recap here. Your x velocity should never have changed. So when we calculated that using cosine, that's our that direction velocity the whole time, right? Our y direction velocity is changing depending on where in the trajectory it is. I don't actually know where in the trajectory it happens to be. That isn't really relevant right now. But we can just calculate its final velocity using one of the kinematics formulas because we know initial, time was given, and gravity is a constant. So, which formula are we using? Minus 1/2 of at squared. That's not a formula, is it? That's not one. Okay. It's been a while. You guys have one of the sheets. Do we have one where it's like A equals
VF minus VI over T?
That's what I was thinking. VF minus VI over T. No 2T or times by 2, right? That's a different one. It's just this one, right?
Yes.
Okay. Okay, so let's plug these in. By the way, this time around, because of kinematics, we do need to account for the fact that our acceleration is going in a different direction than our velocities. So solve for VF. Minus 9.81 times 2.5 plus 8. I got minus 16.5-ish. When I first started drawing the triangle, I wasn't sure whether 2.5 seconds was still on the way up or on the way back down, but I think now we know that 2.5 seconds later means it's back on the way back down again. It really wouldn't have impacted the way we solved the question, because now we know our velocity final here is negative 16.525. We need to find the hypotenuse. So Pythagoras theorem this thing. Verbs here. So if you still have it in your calculator, that 13.856 number, square it. Add 16.525, square it. Square root, should I? That's what I got. Is it there? Okay, cool. Yay for kinematics. Bring back some memories of our first couple weeks of school. Okay, after doing all that work, so long as we didn't make a mistake, let's try using energy instead. Now, it's not going to be way faster, but I bet you'll agree with me on this, that if we used energy instead, this might have been more efficient.
Greg Burrows, Tia Davis, please come to the office.
So we should also be able to use energy instead. So let's redo the entire question on the second sheet here. See if we get the same thing using energy. So, similar sort of trajectory. You're launching this thing at 16 meters per second. We want to try to find its velocity at this point right here. Okay, when you launch this thing, what sort of energy does it have when you launch it? Kinetic, yeah. I mean, we didn't actually get the information for some sort of spring, so let's say that before we started, it's going to have some kinetic energy, and that's pretty much all it has. Is there a little bit of energy relative to the ground? I guess, but we're just going to have to assume that like where it's launched from is more or less ground level. Later, it's still in motion. We know it's on its way back down again. Well, at this point here, rather than write this in, this is our velocity initial squared. Later, it's going to have a velocity final, but it's also going to have some potential energy because it's still up in the air. Does that make sense? So, to begin with, it has potential or kinetic energy to start with, and we actually have the information we need for this. Later, it's going to have a velocity final, but there could still be some
Savannah
potential
Ryan,
left over.
Corbin Robert, please come to the office.
In terms of information we're looking for here, we are solving for the speed of the rock when it's done. So we're looking for velocity final. We weren't given the mass of the rock though. That doesn't matter. There's mass in this example right here. That is the mass of the rock. There's mass right here. That is also the mass of the rock. There's another mass right here, the mass of the rock. So if you wanted to, you could factor out this mass right here, and basically all of these masses should cancel. So its mass was actually irrelevant. Do we know the velocity initial? 16, wasn't it? We don't know velocity final. That's a plus sign. We know gravity. Okay, there is still one thing we're missing. We don't know how high it is above the ground. But if we can find that, then we're golden. Okay? So we just need to try to find a way to find out how high above the ground will this thing actually be. So to do that, we actually have to do a little bit more kinematics. You know how in the previous question, we found in the y direction, the velocity initial in the y direction, the velocity final in the y direction, the acceleration, but we just skipped finding the distance in the y direction.
What are you guys doing right now?
Okay, let's calculate the distance in the y direction now. So I'm going to re-go up and rewrite those variables we did just a little bit ago here. The vi, like these ones right here. I wonder if I can even just cut them. Select. Copy. Paste. Let's do it through. What's one I'm missing? Acceleration in the y direction, negative 9.81. Let's find the distance in the y direction. So to calculate this, we need what? D equals VIT plus 1/2 of AT squared. All right, velocity initial in the y direction was 8. Time we were traveling for was 2.5. 1/2 of negative 9.81. And then our time was 2.5 squared. Thanks, Mike. You guys calculate that too? Okay, another thought here about this then. We have to change the diagram of our problem here. That distance that we calculated being a negative 10 meters means that when we shot it up in the air, it not only has reached the spot where it's like back down there, but we must have shot this off of like a bridge or something like that because it's now lower than it was before. Does that make sense? Like if I were to draw this diagram one more time, when we shot this thing, we shot it up like this, and it's actually now down here by like 10 meters, give or take. That makes sense. I didn't know that at the time. Now we've actually figured that out. So it means I need to change the way I do the question a little bit here. Right here, if we now consider like this level here to kind of be our new floor, if that makes sense. When we launched this thing, it didn't just have kinetic. It actually had kinetic and it had some extra potential. So like to begin with, we had 1/2 of mv squared and some height. And then back over here, then it only has kinetic. You know what I'm saying here? We have to take our potential energy from the after and put it back on the beginning instead. That's all. It doesn't change a whole ton. Just have to kind of rewrite it a little bit here. So when it started, it had kinetic and it had some potential, and then here later it's going to just have some kinetic relative to where it's at right now. Could it keep falling? Sure, I guess, till it hits wherever the actual floor is. You can still cancel mass, that doesn't change, right? Okay, let's plug this in. 1/2 of our velocity. Well, our initial velocity is not directional dependent. If it's an energy, remember how energy is a scalar? I don't care whether it's the x or the y velocity. I just want the actual hypotenuse, the 16, right? Like we're still using the 16 right here. Gravity 9.81 times the height, which I had calculated as 10.65625. Is that right? And then afterwards, 1/2 of v squared. So solve for v. I'm hoping if we did it right, we get the same number twice. What did we calculate before? Somewhere in here. 21. Hey, I got the same number twice. 21.56561209, give or take. Alright. Based on our sig digs then, it looks like we're getting 2. So, I mean, if you were asked to solve this, I did all this exercise to prove you could do it 2 different ways. You know, I mean, ideally what I'm asking you to do now is don't do the kinematics method, practice using energy. So if you just got asked to solve this, your answer would be what, 22 meters per second? That's your speed, by the way. We don't actually have a direction to this, but we at least know the speed, the final speed is 22 meters per second. That is not an x direction velocity, that is not a y direction velocity, that is along the hypotenuse, as this thing seems to keep plummeting downwards. Okay, so a quick summary then. When it comes to conservation of energy, there's really not a formula, so to speak. You have to take the formulas you have and make your own, if that makes sense. And sometimes it's just as straightforward as make potential equal kinetic. Right? Those are easy ones, right? Sometimes you have to consider multiple pieces like the 2 boxes over the pulley system. We had to account for the yellow box and the blue box. This one right here, you had to account for the fact that there could be some potential and some kinetic, and then later there's only kinetic. Okay. So long as you can find a way to keep track of what energies are available, and we ignore friction, because that obviously throws a huge kink into the plans. But if you do that, energy is actually a fairly efficient way of trying to solve some of the questions we solved before. So when you guys get questions on your assignments on your quizzes, they may look somewhat familiar scenarios because we're just reusing the old scenarios of inclined planes and pendulums and shooting projectiles in the air. And we're using energy formulas instead. Any questions? You guys good? Cool. Guys, we have one lesson left and we've covered physics 20. Yeah, and it's a really easy one. Why don't we leave that one though until, why don't we take a work day tomorrow, and then on Wednesday we'll talk about power. It's really one formula, it doesn't take very long, it's pretty straightforward. And yeah, basically after that you've got 4 tasks. Do an assignment, do the lab. I'll try to get the lab all pieced together so you guys can start on that. We'll do one quiz, we'll do one unit test. Finish that before Christmas, and we'll finish this course. Sound good? Okay, take a break if you need, because I was kind of talking for quite a while there, wasn't I?
Liam Scott Worthing.